On a September morning in 1977, a machine sits on top of a rocket in Florida. It weighs less than a family car, it runs on less electricity than a light bulb, and it's leaving the world that built it forever. The people watching from the beach see fire, noise, and a column of white smoke climbing into the blue sky. None of them can see the stranger truth underneath the spectacle. This small, fragile machine is going to outlast almost everything around it. The country that launched it, the language spoken at the launch pad, eventually the stars themselves. Voyager 1 lifts off from Cape Canaveral on September 5, 1977, aboard a Titan III rocket. The launch window is tiny and chosen with obsessive care. Once every 176 years, the outer planets line up in a way that lets a single spacecraft borrow the gravity of each world it passes to throw itself toward the next. Skip that window, and the mission becomes impossible. The engineers knew they were building for a moment that would not return in their lifetimes. The spacecraft itself is compact, a 10-sided aluminum frame with long booms reaching outward, carrying instruments like limbs. Its main antenna, a dish more than 11 feet across, points back toward Earth. It always will. Bolted to its side is something that has nothing to do with planetary science. A 12-inch gold-plated copper disc. On it, music from a dozen cultures, greetings in 55 languages, the sound of rain and surf, and a mother's first words to her child. Diagrams that explain where Earth sits among the stars, with instructions for playing the record etched into the metal itself. A message in a bottle dropped into an ocean with no shore. The team gave Voyager instruments to see and a record to speak. Then they aimed her at the outer dark and let go. By the end of this video, you'll know where this machine ends up. Not in 100 years, not in a million, in 10 trillion, when the last stars in the universe are burning out. The journey starts with the two biggest worlds we have. 16 months after launch, the black between worlds gives way to something enormous. Jupiter grows in Voyager's cameras slowly, a pale smear that swells over weeks into a banded, churning colossus. By the closest approach in March of 1979, the pictures arriving on Earth look like nothing astronomy has ever produced. For centuries, Jupiter had been a calm point of light in a telescope. Up close, the planet is in constant, violent motion. Cloud belts grind against each other, driven by winds faster than any hurricane ever recorded on Earth. The Great Red Spot, a storm that has raged for centuries, sits embedded in the southern hemisphere like an open wound, wide enough to swallow our entire planet with room to spare. Beneath those cloud tops, lightning flashes continuously. Not the thin forked bolts we know, but superbolts carrying millions of times more energy. And Jupiter itself is only half the story. As Voyager swings through the system, the cameras turn toward the moons. Io, the innermost of the large ones, was supposed to be a dead, cratered ball of rock. The images stop scientists cold. Umbrella-shaped plumes rise off the surface, active volcanoes erupting on a moon. Io turns out to be the most geologically violent body in the solar system, kneaded and heated by the gravity of Jupiter and the neighboring moons until its interior stays molten. Eruptions paint the landscape in sulfur yellows and reds, and the terrain changes from week to week. Europa offers a quieter kind of shock. The surface is bright and almost unnaturally smooth, crossed by dark reddish lines and overlapping networks that match no crater pattern and no volcano. Cracks, in other words, as if something underneath the ice keeps moving, pressing upward, refreezing. The implication, whispered in 1979 and shouted in the decades since, is a hidden ocean of liquid water sealed in cold and darkness far from the warmth of the sun. Ganymede shows two faces, ancient dark terrain scarred by early impacts, next to younger groove bands where the ice has shifted and reset. Callisto seems frozen in time, its crust recording 4 billion years of collisions like a ledger of catastrophe. Then Jupiter does for Voyager what no rocket could. The planet hands over speed. Swinging behind the giant, the spacecraft borrows a sliver of Jupiter's own orbital momentum and exits the encounter faster than she arrived, aimed at Saturn on a path no amount of fuel could have bought. Physics offers, Voyager accepts, and moves on. Saturn arrives in November of 1980, From a distance, the rings look solid, a flat disk of light around a pale beige planet, clean and geometric, like something drawn with a compass. Up close, Voyager's cameras dismantle that picture entirely. The ring system is not one disk, it is thousands of individual ringlets, each a separate stream of particles, mostly water ice, ranging from dust grains to boulders the size of houses, every piece tracing its own precise orbit. Between the rings sit gaps. Within them run waves, braids, and sharp edges, all maintained by the gravity of small moons embedded in the system. Some of those moons work as sculptors. Prometheus and Pandora flank the narrow F-ring and keep it confined with their tugging. Pan sweeps its own lane clean. Mimas carves out the wide Cassini division through orbital resonance, the mathematics of gravity written in ice and rock where anyone can see it. Saturn's magnetic field turns out to be smaller than Jupiter's but still enormous next to Earth's. Voyager's instruments map its reach, recording the energetic particles trapped inside and the way the solar wind squashes the field on the day side while stretching it into a long tail behind. The moons here form a gallery of oddities. Mimas carries an impact crater so large relative to its size that whatever hit it came close to shattering the whole body. Enceladus gleams, reflecting nearly all the sunlight that touches it, the signature of a young and active surface. Each one is a world in miniature, shaped by its own private history. But Titan is the reason Voyager bent her path the way she did. Titan is Saturn's largest moon, bigger than the planet Mercury, and the only moon in the solar system wrapped in a thick, permanent atmosphere. From orbit, it shows nothing, an orange-brown haze so dense the cameras cannot find the ground beneath it. What the instruments can do is taste the air itself. Nitrogen, mostly, much like Earth's, laced with methane, with heavy organic molecules forming in the upper layers as ultraviolet light breaks simple compounds apart and the fragments recombine into something stranger. Standing on Titan, a person would feel about 1.5 times the pressure of sea level on Earth. The cold is another matter. At minus 290 degrees Fahrenheit, methane behaves the way water does here. It can fall as rain, pool on the surface, carve rivers and deltas into a bedrock of solid water ice. Not life, but chemistry, and chemistry with enough time and energy has a habit of becoming interesting. The close pass over Titan bends Voyager's trajectory permanently upward out of the flat plane the planets share. There will be no more worlds to visit. Saturn's gravity assist is the last one physics has on offer. From here, the spacecraft is on her own heading. 13 years after launch, someone has an idea. Voyager is now 3.7 billion miles from home. Her cameras have pointed outward since Saturn, and planetary science no longer needs them. Soon they will be shut down for good, to save power for the instruments that still have work ahead. Before that happens, Carl Sagan, the scientist who championed this mission, asks for one final sequence. Turn the cameras around, look back at the inner solar system and the pale warmth of a distant sun. Getting the geometry right takes months, partly to protect the optics from accidental direct sunlight. In February of 1990, Voyager 1 pivots and takes 60 frames across the solar system, a mosaic portrait of the neighborhood she left behind. In one of those frames, caught inside a stray beam of scattered light, sits a point of brightness smaller than a single pixel. Earth. Every person who ever lived, every war, every act of love and cruelty, every discovery, every prayer aimed at a sky that never answered, all of it inside a dot small enough to be mistaken for dust on the lens. Sagan described that picture as a mote of dust suspended in a sunbeam. Not comfort exactly, perspective, a reminder that the rivalries and certainties filling our days play out on a world that, from far enough away, cannot be seen at all. When the portrait is finished, the cameras are powered down for the last time. Voyager stopped looking back. The odometer keeps climbing. Quick pause, because this is where most tellings of the story stop. Everything so far covers the first 13 years of the trip, the part with planets and photographs. What comes next covers the other 10 trillion, and it is the part of this video exists for. How a machine the size of a small car ends up older than the stars. That part begins at an invisible border, 35 years out from the launch pad. For decades after Saturn, Voyager travels without a destination. The Sun's territory does have an edge, though. The solar wind, a constant stream of charged particles blowing outward from the corona, inflates a vast bubble called the heliosphere. Where the pressure of that wind finally balances against the thin material drifting between the stars lies a boundary called the heliopause. No wall, no painted line across the void, but a real measurable transition. Several of Voyager's instruments, still functioning after 3.5 decades, are watching for it. What they catch is a changing of the guard. Particles born inside the bubble, carried out by the solar wind, suddenly collapse in number. Cosmic rays from outside, fired off by distant supernovae and other violence across the galaxy, surge at the same moment. The magnetic environment shifts. This is somewhere new. On August 25, 2012, after 35 years in flight, Voyager 1 crosses the heliopause and becomes the first human-made object in interstellar space. The gap between stars, a region that existed for all of human history purely as a concept, suddenly has something of ours inside it. Measuring it, reporting home at the speed of light, across a distance the signal needs more than 17 hours to cover. And that report arrives almost as a ghost. Voyager's transmitter puts out about 20 watts, comparable to a dim refrigerator bulb. After billions of miles of spreading, the energy reaching the giant antennas of NASA's Deep Space Network amounts to nearly nothing. A whisper caught only because the dishes are huge and the people who built the ground systems knew how to listen for the almost inaudible. It arrives and it gets read. Meanwhile, the power is running out. 3 radioisotope generators keep Voyager alive, converting the heat of decaying plutonium-238 into electricity. At launch, they delivered roughly 470 watts. Every year since, the output has slipped a little lower as the plutonium burns through its half-life. After nearly 5 decades, only a fraction of the original supply remains, and the mission has turned into an exercise in triage. One by one, instruments get switched off, not because they failed, but because there is no longer enough electricity to feed them. Every shutdown is a calculation. What can still be learned, weighed against what it costs to keep a system warm and powered. The engineers making those calls work on hardware built before many of them were born, guided by documentation handed down through generations, each one trained by the one before. Sometime in the years ahead, the available power will drop below the threshold needed to run any science instrument reliably. The transmitter may hold on a while longer, broadcasting an empty channel. At some further point, even that falls silent. From Earth, there will be no dramatic ending, no broadcast labeled final. The signal will simply sink below the threshold of detection. A last data point gets logged, and after it, nothing. Silence changes nothing out there. Voyager keeps moving at about 38,000 miles per hour. Slow by cosmic standards, light travels nearly 18,000 times faster, but relentless. With no friction to fight, nothing slows her down and nothing pushes her sideways. The trajectory written by gravity and momentum in 1977 simply continues, out between the stars, indefinitely. In roughly 40,000 years, that unchanging trajectory brings Voyager 1 relatively close to a small red dwarf called Gliese 445 in the constellation Camelopardalis. Close by interstellar standards means about 1.6 light years. No orbit, no slowdown, no arrival. The probe brushes the outer fringe of the star's gravitational reach and keeps going, unaware of the encounter in any meaningful sense. By then, the civilization that built her may or may not exist. Whole languages have died and been replaced in far shorter spans. The engineers' names in the mission records will be as obscure as the names of the stonecutters of ancient Egypt. NASA, the United States, perhaps the very idea of nations, could belong to an era no living mind remembers. Voyager carries none of that weight. Machines do not age the way living things do, and you cannot forget what you never knew. She's metal moving through emptiness, and the moving continues whether anyone watches or not. The galaxy around her is not permanent either. For billions of years, Andromeda, the largest member of our local group of galaxies, a spiral of hundreds of billions of stars, has been falling toward the Milky Way. In roughly 4 to 5 billion years, the two begin to interact. Calling it a collision is misleading. Galaxies are mostly empty space, and their stars sit so far apart that direct hits are rare. What actually happens is a gravitational reshaping. Stars get yanked from their old orbits and flung onto new ones. The elegant spiral arms of both systems dissolve and blend, and over hundreds of millions of years, the wreckage settles into a single, giant elliptical galaxy. Astronomers have already given it a name: Milkomeda. Voyager 1 will be somewhere inside that process, impossible to pinpoint across such spans of time. A speck of aluminum and gold drifting through a galaxy in the middle of becoming something else. The merger never touches her. She passes through it the way she passes through everything, without notice, without reaction, carrying her golden record across the universe, slowly turning unrecognizable. Because the stars themselves are winding down, the most massive ones burn out in mere billions of years and collapse into neutron stars or black holes. Medium suns like ours last billions before swelling into red giants and cooling into white dwarfs. Red dwarfs, dim and frugal with their fuel, hold out for trillions. Even they run dry. Around 10 trillion years from now, the era of star formation itself comes to an end. The raw material, hydrogen gas collapsing under gravity, has been mostly consumed or scattered. Galaxies that once blazed grow sparse and dark. The universe is not empty, just quiet, populated by remnants. White dwarfs fading towards invisibility. Neutron stars spinning in the dark. Black holes feeding slowly. If the material she is made of survives that long, Voyager 1 will be older than nearly every active star that ever existed, crossing a cosmos that no longer resembles the one she launched into. No bright suns to steer by, no solar wind marking anyone's territory, just the long, cold expansion carrying everything farther from everything else. Physics may not allow even that to last forever. One theoretical possibility, never observed but permitted by certain models, says protons, the particles anchoring every atomic nucleus, are not perfectly stable across spans that make the current age of the universe look like an instant. If so, ordinary matter slowly dissolves. Atoms come apart. The aluminum frame, the gold-plated copper disk, the silicon in the circuits, all of it would unravel particle by particle into radiation and the lightest scraps of matter. There would be no destruction in any dramatic sense, just a fading, stretched across durations with no human analogy, until the spacecraft has melted into the expanding dark. And yet, what she carried never depended on her physical survival. The record is a copy. Its contents were transmitted, archived, studied, and shared long ago, stored in something far more durable than copper and gold. The minds of people who read about her, built things inspired by her, looked up and decided that reaching outward was worth the effort. Voyager 1 was never just hardware. She was a decision. The decision to try without certainty of success, without expectation of return, without a single guarantee that the message would ever be found, because the attempt itself was worth making. She reached past every planet, crossed the boundary of the solar system, entered the space between stars, and kept sending data home until there was nothing left to send. The signal will fade, the sun will cool, and the galaxy she crossed will go ancient and quiet. Somewhere out in the dark, she will still be moving. She always will be.